Okay, hi everybody, this is Dr. Schultz, and I'm going to present a brief video lesson this morning on target 3.3c, which is I can calculate the value of the gravitational acceleration, g, given the mass and the radius of a planet. And the expectation here is that you guys will take notes on this, so I hope you're ready. The material that I'm going to talk about is also covered in the physics classroom. It's lesson 3 on universal gravitation, part E, which is the value of g. Okay, so why don't we get started here. We're going to start off with writing down the formula for universal gravitation. This is a formula that we learned earlier. And now what we're going to do is when we write it, we're going to write it to express the force of an object, or I should say the force on an object which is near the surface of the Earth. So instead of using m1 times m2 over r squared, I'm actually going to substitute in and talk about the mass of an object and the mass of the Earth, because those are the two objects that are attracting each other. Now for the r squared, I'm going to use the radius of the Earth as the distance. And to understand why, we just think about the fact that for most objects near sea level, their separation from the center of the Earth would be equal to the Earth's radius. Okay, and really that's a pretty good assumption. Even if you're going to go up into a tall building, you're really not changing that distance very much. So we're going to use the radius of the planet as the radius in this formula. Okay, now our goal is to use this formula to somehow come back to the little g that we've learned about earlier in this course. That is the 9.8 meters per second squared g. So how are we going to do that? Well, let's go back to the formula that we have been using to calculate the weight of an object. So W is equal to mass times gravity. W equals mg. And for the mass, we're going to stress that we're calculating the, we're talking about the mass of the object, maybe an apple, for example. And the idea is that the weight that you calculate with the formula at mass times gravity is actually the same force that you would calculate with the law of universal gravitation, which is given above. So I can actually set these two formulas equal to each other, and then I can use that expression to solve for little g. And so that's what I'm going to do. So if you set the two expressions equal, on the left side you have mg, where m is the mass of the object, and on the right side you have the law of universal gravitation written between an object and the Earth, okay, assuming that the object is at sea level or near it. And one of the things that you notice right away is that the mass of the object cancels out. And that cancellation is significant because it means that the mass of the object really has nothing to do with its acceleration towards the Earth. That acceleration is going to be approximately constant. And so when you cancel out the mass of the object, you're left with a nice formula for calculating the acceleration of gravity near the surface of the Earth. That acceleration depends on three things. First of all, it depends on the universal gravitational constant, big G, which we know is a very small number. Second of all, it depends on the mass of the planet. In this case, we're considering the mass of the Earth. And that's a big number, which tends to cancel out the smallness of the big G. And finally, we have to divide by the radius of the planet squared. And so this is where the inverse square comes in. And we're using the radius of the planet to do that. So this formula is it's a very useful one. You can use it to calculate G on Earth. You can also use it to calculate the free fall acceleration on any planet that you'd like. But you have to know the mass of the planet and you have to know the radius of the planet in order to do so. So you guys will be doing some calculations in your homework in which I have you calculate the free fall acceleration on the Moon and on Jupiter and on different planets just to try this out. Okay, so this formula is generally useful. It's not just for the Earth. You can substitute the mass of any planet and the radius of any planet to find the free fall acceleration. So we're going to end this video And at the bottom of the screen, I'm going to provide you with the mass of our planet Earth. Okay, it's a very large number. It's about 6 times 10 to the 24th kilograms. And the radius of the Earth, which is about 6 million meters. Okay, in the next video lesson, you'll learn about where those numbers come from. But for now, what I'd like you to do is take out your calculators, and I'd like you to actually plug those numbers in. And I'd like you to verify that when you do the calculation, that you get about 9.8 meters per second squared for the Earth's free fall acceleration. Okay, so I'm going to end the video here. I would like all of you to try this, and if you're unable to do it, help each other. And it may be an issue of using parentheses properly, or dividing, or using scientific notation, but just help each other out with that. Okay, so we're going to stop this video, and the next video that's coming up is on finding the mass of the Earth and finding the universal gravitational constant. Alright, have fun.